Hey there. So for the next few minutes, I'd like to talk to you about some of the rules of counting, how to count. And if that sounds weird for you in a slide deck about probability, well then here's the connection. If I'd asked you, what's the probability that if you pull one card out of a deck of 52, what's the probability that it comes up an ace? Well, you know there's four aces, but you could count them, 1, 2, 3, 4. Out of, well, 52 possible cards, and you could count out all of those 52. So you would count out 4 and then divide by counting out the 52 cards. So in the numerator and the denominator of any probability question, you can usually think of it as a counting problem. Now there are university courses devoted to the mathematics of counting. And that sounds embarrassing, so they have renamed the courses from counting to something called combinatorics. But really, it just boils down to counting. And there's a couple of rules that just seem to come up over and over when we're doing probability, and that is counting the different ways that we can reorder a set, counting how many different ways we can have combinations of things, and counting how many different ways we can rearrange a subset. It's called a permutation. So let's dive right in. So let's say that you're asked to reorder three things, A, B, and C. Now I think all of you could do this, but I'd like to lead you through a structured way of doing this, because I think it's going to help us figure out a formula for a more general case. So let's work through the simple example first, using something called a tree diagram. So here it goes. We'd like to reorder three things, so they're going to occupy three different places. Now, our first place, we might choose to start off with A's and have like A, B, C, A, C, A, C, B, A, B, C. So let's say we could do A, we could do B as our first place, or we could do C. Now let's suppose that we've committed to A. Now how many different ways could we order the remainder? Well, if we've already used up A, then we could either go B or we could go C. And now once we figured out A and B, well, in this particular ordering, there's only one way to go. It's got to be C, which gives us this particular ordering. We could have gone A, C. Now what's left? Got to be B. So A, C, B. All right, we've got 2 out of a whole bunch of different reorderings. Let's keep doing this tree diagram. If we start off with B first, then we could go in one of 2 different ways. We could either choose A for our second place or C for that second place. Now, if we have B, A, then we know the third one's got to be C, leaving us with B, A, C. And then here, B, C, it's got to be A. B, C, A. And then finally, what if we had started out our ordering here with a C? Then again, we could have 2 different options. We could go B or A. And if we had C, B, that one's got to be an A. Or C, A, got to be a B. So here we go. We have all of our possible orderings. In doing this in kind of a tree diagram, in the systematic way, helps so that we don't leave one out. Right? If we just, rather than brute forcing it and jumping towards this, if you systematically work through the problem, we know we won't overlook anything. But it does something else for us. It might help us figure out a formula for a more general case. Let's see if we can figure that out. Now, we were trying to figure out a way to order 3 different things. And when we first started out, in this first case, we had 3 options. We could have picked A, B, or C. So we had 3 options. But once we've committed to one of those, let's say we picked A, then we were left with only 2 options. Likewise, if we had chosen B, then we had these two options. Or if we had chosen C, we had those two options. So for this second place, we really only had two options given our first one. So we have 3 times 2 for 6 total ways we could have gone by this point in our process. Now what about the last place? The last place is a gimme. If we knew A and B, then there's no choice anymore. It's guaranteed to be C. So how many choices did we have? Well, 1, which is to say we didn't have a choice. So how many orderings do we have? 3, 4, 5, 6. But that's also equal to 3 times 2 times 1. You might recognize this kind of thing of multiplying by a decreasing number like that. It's called a factorial. So 3 factorial is defined to be 3 times 2 times 1. And this exclamation point is how we're going to denote the word factorial. So, for example, if I had asked you to reorder 4 things, A, B, C, and D. All right, so that's 4 spaces to figure out. For our first place, well, we can choose any one from these 4 things. So we have 4 options. But once we've picked one of those, let's say we picked B, well, now we only have 3 for our second place term. Let's say it was D. Right? So once we pick B and D, now we only have 2 options left. And then no options left, just 1, right? It's not an option. And so we have 4 times 3 times 2 times 1. So that's 12 times 2 is 24 times 1 is still 24. That is called 4 factorial. Right? 4 times 3 times 2 times 1. I think that kind of hints at a very general kind of formula. That if you have n things, and you need to order them in as many ways as possible without reusing any of our terms, then that is equal to n factorial different ways that we can reorder something. We're going to use this, again, for more complicated cases. Let's see. This time, I'd like to reorder the items in a list, but I'd like to only focus on a small subset from that bigger list. That sounds abstract. Here's what I mean. Let's do this reordering business, but let's say that we now have a set of 5 people, so a larger set. So some set n of size n. Here we got n is 5. 1, 2, 3, 4, 5 people. And we'd like to come up with an entire listing, or at least being able to count how many different ways we could order 3 things. So, for example, if I wanted to take 5 people but award first, second, and third prize, how many different ways could we do that? And so here, order matters, because if you're person A, you'd rather be first place, not second or third place. So we're still doing reordering. And when we talk about reordering a subset, that's called a permutation. It's really just a reordering. It's another fancy word for reordering, permutation. So let's use the same kind of formulaic thinking we did in the last slide here. Now we'd like to award first prize. We could award it any way we wanted to, but we have 5 options, A, B, C, D, and E. Now, once we've figured out who's first place, like let's say it's person B, doesn't matter, but just say it's B, then how many options do we have left? Well, for second prize, we only have 4 options. Let's say we chose to use person C for second place. Now, how many options do we have for third prize? We only have 3. 3 different options for third prize. So that's it. How many different ways can we reorder 3 out of 5 people? It's 5 times 4 times 3, which is 60. And this is also why I didn't do that tree diagram. That'd have been a really complicated tree diagram with 60 different outcomes. You can also see why the formulas are so useful. But speaking of formula, can we come up with a general formula for how this works? Let's try this on for size. When we were trying to figure out all the different ways that we could order something, we had 5 times 4 times 3. That kind of sounds like what we had going on in the previous slide. That almost looks like 5 factorial. But it's not quite 5 factorial, because it's 5 times 4 times 3, and 5 factorial would have the 2 and the 1. So how can we express 5 times 4 times 3 while taking advantage of this factorial type notation? So try this on. 5 times 4 times 3 is really just another way of saying 5 times 4 times 3 times 2 times 1, so the 5 factorial, but then divide by 2 times 1, in which case the 2 cancels, the 1 cancels, leaving us with 5 times 4 times 3. So this kind of truncated factorial, you can express it as the ratio of 2 different factorials. Specifically, this way of permuting three out of 5 is equal to 5 factorial divided by 2 factorial. In fact, we're going to see that this is kind of a general formula. If we had a set of n items, and n is no longer 5 now, it can be any big set of things, and we want to know how many different ways of reordering a subset is, then our formula is the ratio of 2 factorials, right? We have n different items, so we could choose n of them, n minus 1 of them, n minus 2 of them, and so forth. But then we kind of truncate, and we don't keep on going. And the way we do that is by dividing through by those terms that we don't need. Now, how many terms is it we don't need? We're ordering x of them. Once we've used x of them, the ones we don't need are the ones that are left over. It's the n minus x of them. And we know from our first slide how many different ways can we reorder n minus x things? It's n minus x factorial. Okay, so that's what we're doing right here in this denominator. We are eliminating all of the different ways that we can reorder the stuff we don't care about. The leftovers, 4th and 5th and 6th place, and so forth. I'd like to point out also just a little bit of notation. This notation is fairly common. It's just a way of saying we have n items, and we'd like to figure out how many different permutations or reorderings of x of those n. So it's read n permute x. N permute x, which is also another one of those ways that you might see it in your textbook. Okay, let's get to our final counting rule. This one's called combinations. In this case, we don't care about order so much. So we're going to treat A, B, C in exactly the same way as C, B, A. So here's an example. Let's say you're at a playground and you have 5 people, A, B, C, D, and E. And you're wondering, how many teams of 3 could I make? Not to play against each other. I just mean if you're going to play with, if 3 people are going to play together, how many different groups of 3 can there be? So it's similar to a permutation question, but order is not allowed to matter anymore, which means we actually have to eliminate a whole bunch of different cases. So since we can't treat A, B, C the same as C, B, A, we need to remove one of those from our overall counts. So I think permutations is probably a great way to start for us to understand combinations. Let's think of this for a second as though it were a permutation question, where we're wondering how many different ways can we permute 3 out of 5 things. So 5 permute 3. So here's a total listing of all of the different permutations, and I've kind of grouped them here for a reason. If you check out over here with the top left item, you'll see that all of these are different permutations of the same 3 terms. Likewise, for example, all of these are variations on B, D, E. So we can start off with our total set of different orderings, different permutations, and then strive to eliminate all of the combinations that we don't care about, or I should say all of the different permutations. So what we're going to want is, if I can just clear this out, we're going to want just the combinations, those items in black, rather than the original, all of the different permutations. So it's going to be a much more restricted sample size or count size. So I think this is the best way then to think of the combinations formula. The combinations formula looks just like the permutations one, except we're adding this term in the denominator, right? We're taking our permutations of n permute x, or sometimes you'll see it n permute x, and we're going to eliminate a certain number of these. So we're going to divide them out from our total count. So how do we do that? So x factorial, now what is that? That's the size of the individual little teams that you're making up. So in our case, we were making up teams of size 3, which means we can reorder those 3 things 3 factorial different ways for a total of 6. In general, if we were making teams of size x, then we could reorder all of those different things, could permute them x factorial different ways. So here's how you would do combinations then. We'll read this n choose x. Well, sometimes, by the way, often abbreviated like this. Looks like a fraction, but there's no little dash in the middle. So it's n choose x, which means we're going to take our overall number of permutations, but then we're also going to divide out the permutations within each of our groups, leaving us with this little formula. Let's go back a couple slides. When we were here, right, we had 10 items, 10 of these blocks. But how did we get there? We had overall 60 different ways to permute, so 5 permute 3, that's our 60. But then within each of these teams of 3, we got 3 unique letters. We could permute each of these 3 times 2 times 1 ways. 1, 2, so that 3 times 2 times 1 is 6. In here, sure enough, we have 1, 2, 3, 4, 5. 6 different permutations within each group. So that's what we need to take out from our total list of 60. Let's take a brief second to just look at our formulas and try to see the relationship between them a little bit more clearly. So I've got here up on top the formula for permutation. and the formula for a combination. Now, we just talked about how you can think of a combination as a restriction on the number of permutations. That set of permutations is really huge because it doesn't include just, let's say, ABC, but it also includes CBA and CAB, includes all those other things. And if we're not supposed to consider that for combinations, we need to remove them somehow. So we're going to divide through so that we get a smaller number, right? So we're dividing through by all of the different ways of permuting our individual little groups that we've chosen, that we've created. So that's one way to think about it, as combinations as being a restriction on permutations. The other way that you might want to think about this is if we cross multiply this x factorial and bring it to the other side, we have this formula. And if we view it in this way, you can think about a permutation as follows. You've got your groups, but they're unordered, right? You've got your combinations, but order doesn't matter. And now we would like to rearrange inside all of those groups. So we would like to expand our set. So you can think of a permutation as taking your combinations and then multiplying it by all the different ways that you can rearrange your combinations. All right. Okay, so we've just learned some counting rules. Let's make it explicit about what this has to do with probability. Let's work out an example with the Lotto. So a simple Lotto would be a pick six, where you have a set of, let's say, 49 numbers, and you need to pick 6 of them. And hopefully the 6 numbers that you picked are the numbers that get pulled once a week from the big Lotto drawing. So what are the chances that you would win the Lotto? Well, we need to count how many different possible ways to pick 6 numbers out of 49 are, and then your chances are 1 out of that number. So we need to do some counting. So this is a combinations problem because order doesn't matter. In other words, you've got your bubble sheet with 49 numbers, and you've got to fill in some numbers. But that's it. It's not like if you filled them in this order, it's a different thing than if you filled them in the other order. So we're not talking about permutations. This is a combinations problem. We have 49, and we want to choose 6. How many different sets of 6 could we get out of 49 numbers? Well, that's 49, choose 6. And so according to our formulas, this would be 49 factorial divided by 6 factorial times 49 minus 6 factorial. In other words, this part here is the permutations part, and then this adjustment eliminates all those redundancies, making this a combinations problem. If you plug this into a calculator, you would get 13,983,816 different ways that you could have filled out that bubble sheet. You filled out one of them, so your chances of winning the Lotto are 1 out of 13.9 million, which is a really small number, kind of close to 0%. All right, so now that you get the hang of this, let's do the Powerball. So here's how the Powerball works. It's kind of like a pick six, but just a little bit more complicated. Here, you're going to be picking 2 sets of numbers. You're going to be picking a set of 5 numbers out of a set of 69, but then you're also going to be picking 1 additional number out of a different set of 26. Now, what you do in the first set is different from what goes on in the second set. These are 2 independent things. So we're going to be using the multiplication rule to figure out some probabilities. So what is the probability of winning the Powerball? How do we figure that out? Well, the first part is that we're picking 5 out of 69. So that is a combinations problem. 69, choose 5. And then we're going to multiply that, multiplication rule, by 26, pick 1. Now let's simplify this thing. So we have, for our first term, 69 factorial divided by 5 factorial over 69 minus 5 factorial. And then we're going to multiply by this second term. We'll see that that's just equal to 26. But let's work it out. We get 26 factorial divided by 1 factorial, 26 minus 1 factorial. Let's keep simplifying. 69 factorial is 69 times 68 times 67 times 66 times 64, and so on. 5 factorial is 5 times 4 times 3 times 2 times 1. 69 minus 5 factorial, that's just 64 factorial. So 64 times 63 times 62. Okay, so there's our first term. And then we multiply by 26 factorial, which is 26 times 25 times 24 times 23, and so on. 1 factorial is just 1. 26 minus 1, that's 25. So 25 factorial is 25 times 24 times 23, and so forth. We'll see that a lot of this stuff cancels. For example, in this first term, 64 cancels with 64. In this dot, 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 we had 63 times 62 times 61. So all those cancel with these. So this is not bad. This is just 69 times 68, 67 times 66 times 65 over 5 times 4 times 3 times 2 times 1. And then our next term also simplifies. 25 times 24 times 23 in the denominator. This part here cancels with these guys, leaving us just with 26. So we can just key this into a calculator and get our answer. And if we do, we get a very big number. The number that we get is 292,201,338. So that's how many different possible combinations of these numbers we could have. And if you only have one of those tickets, then your probability of winning is 1 over 292 million, or 1 out of 292 million. That's a really low probability of winning the Powerball. So good luck with that. Thanks for listening. That's all we got for today.